In this tutorial, we will consider the structure of output files for a more complicated case than what was considered in the tutorial structure of output files 1. It is recommended that you watch the first tutorial before watching this one. So in here I have set up a set of parameters. The composition which we are using has several different trace elements, but as you can see, it doesn't have any volatile elements. Water, carbon dioxide, and sulfur are not present in the composition. In terms of the minerals which we selected to participate in calculation, there is olivine, plagioclase, clinopyroxene, orthopyroxene, and note that we also added sulfide and fluid. So obviously, since there is no sulfur and water or carbon dioxide in the composition, these are not going to form, and the implication of this for the structure of the output files we will consider later. We also defined variable extent of fractionation, so some proportions of the minerals will be remaining in the magma together with the melt, and then the other part of those minerals will be moved into the cumulate. As you note, orthopyroxene is fractionating 100%, nothing is left in the magma if it is forming, and I just note that these are just the numbers I've chosen for this example. They don't mean to indicate sensible numbers for modeling fractionation of this particular composition. We also will have changing pressure during calculations as a function of the extent of crystallization, and we will consider the implications of this in the output files, and we will model this to the extent of crystallization of 70%, so 30% of melt will be left. So I'll start calculation now and then pause the video until the calculation is completed so we can look at the results. So now the calculations are completed. Let's have a look at the results. What's important to note is that now, because we are not doing 100% fractional crystallizations, you can see that in the magma we have melt, and towards the end, as we said, it will be 30% of the melt. We also have some amount of olivine, we have plagioclase, and we have clinopyroxene, and in the cumulate we have all four different minerals, and these are the proportion of those minerals in the cumulate. And just to remind you, this is a combined composition of the cumulate, and these are bulk composition of each phase in the cumulate, where at the upper part of the output on the screen here we have the compositions of minerals which are currently in equilibrium with the melt. Now, before we export to Excel, I just wanted to note that for this calculation I didn't save the composition of cumulative phases, and I didn't export elemental concentration to files either. So let's have a look at the structure of the files. As before, the first sheet is showing us all the calculation parameters, including the distribution coefficients that were selected for that particular calculation. Now let's have a look at the structure of the main output file. If you remember, the first set of columns here is for the magma composition, and because we have selected a number of trace elements in the starting composition. Now this is the number of columns which characterizes the magma composition. Because now there are minerals in the magma, in addition to the melt, the composition of the magma is different to the composition of the melts. It's a sum of the composition of the melt and minerals. And just to remind you, every row in this file is an intermediate state of the system, and we requested that each 1% of crystallization is reported, and so at the end we have, in this case, 76 rows. So after the composition of the magma, we have the composition of the melt reported, and for both magma and melt, the column with oxygen now reports the amount of oxygen which is required to balance all of these elements in the melt. So the major elements are reported as oxides, but the trace elements are reported in ppm element, and so this is the oxygen which is required to combine with all of those elements. These are followed by the columns with the cumulate, and again it's exactly the same situation. There are major and trace elements in the cumulate. Oxygen column is showing the required amount of oxygen in the cumulate to balance all the elements. And again, at the following the cumulate, we have temperatures. So the first column is the actual accepted temperature of the melt at this state of fractionation, and then the next 4 columns in this case are the pseudo-liquidus temperatures of the minerals which were participating in the calculations. And if you look towards the end, all 4 of them have effectively the same values, which means that they're all crystallizing together, and that's the accepted temperature. And then earlier we would have only olivine and plagioclase crystallizing together, no pyroxene. Then Kleiner pyroxene would join in, and then you will have 3 temperatures effectively the same, and only orthopyroxene at a low value, and we've discussed this in detail in the previous video. Now this is now followed by the compositional parameters for the phases which are present in magma. And if you notice in here, we have compositional parameters for the immiscible sulfide melt, fluid, and the sulfate. Now they are in the files because we have chosen those models for those minerals in here, as I mentioned previously. And even though clearly they wouldn't be forming because there are no volatile elements in the melt, because they were chosen, the columns for them will appear in the output files. Now, if you don't want them to be part of your output, then you simply do not select them. And if you remove them, then sulfide columns will not appear. So it's up to you whether you are more interested in keeping the same number of columns always, or you would want to have only columns which can potentially have values. After the compositional parameters for phases in the magma, we have columns which show compositional parameters of phases in the cumulate. And again, initially we'll have olivine because it appeared first, then plagioclase will join, then Kleiner pyroxene, and then orthopyroxene will join later. The next column is pressure, and for this particular calculation we made pressure change with extent of crystallization. What was set in there is that the first 30% of crystallization pressure remained constant 5 kilobars, and then we modeled ascent to 0.5 kilobar at the end. So pressure was progressively decreasing as the crystallization proceeded. This follows with oxygen fugacity as absolute values and delta QFM, and melt density and viscosity. And now the important set of columns here are the proportion of phases. So now we have minerals both in the magma and in the cumulate. And I would like you please to pay attention to these columns here, which indicate whether peritectic were occurring at this stage of crystallization or not for each mineral which was present in the magma. Now, if you would like to better understand what peritectic is, you can have a look at the manual, and it has references in there. But the important point I would like to emphasize, when peritectic occurred, that Y, meaning yes here, means that olivine was dissolving, and in this particular case olivine was dissolving because orthopyroxene was crystallizing. If you notice, olivine started dissolving when orthopyroxene started crystallizing, and that's a very well-known peritectic reaction. You also can see that clinopyroxene was dissolving at some stage, again reacting with orthopyroxene. So this is important information for you to think of the process occurring during crystallization. The implication for this is that in the percentages of minerals you will see certain different behavior if peritectic occurs. So for example, if we look at olivine, its amount in the magma is increasing as crystallization proceeds until the moment peritectic occurs, and then you can see that the amount of olivine in the magma is actually decreasing despite crystallization proceeding. And you know that crystallization of olivine is proceeding because in the cumulate, which is this column here, the amount of olivine keeps increasing. This is the olivine which is separated. So we know that we have peritectic reaction occurring when olivine is dissolving, and orthopyroxene is the reason for that dissolution. So we now have values for olivine, plagioclase, and clinopyroxene in the magma, and the values for those minerals in the cumulate. Let's have a look at the very last line in this output. So if you have a look at the orthopyroxene, which is this column, we set 100% of fractionation, so all orthopyroxene is in the cumulate. There is 0 in the magma. If we look at clinopyroxene, which is this column here before orthopyroxene, they're almost the same, but in the magma it is a little bit less than in the cumulate, and this is simply because that we had some peritectic reaction occurring during earlier stage of fractionation, which led to a small decrease in the amount of clinopyroxene in the magma. And if you remember, we said 50% fractionation, so if peritectic didn't occur, we would have exactly the same numbers for the amount of clinopyroxene in the magma and in cumulate. With plagioclase, we said 80% of it remains in the magma and 20% fractionates, so you can see that this is a quarter of this value here. Most of plagioclase is in the magma. And with olivine, it's the reverse. 80% of olivine was forming and being removed to the cumulate, and a little bit of it was remaining in the magma. And remember also it was dissolving towards the end when orthopyroxene started crystallizing. So if we would like a summary of the results, altogether in cumulate we had around 28% of the initial composition, and these are weight percent, not volume percent. In the magma we had 30% melt and almost 42% are crystals in the magma. So towards the end of crystallization there were more crystals in the magma than melt, and then initial 28% of the crystals were in the accumulate. So this is the structure which we have for the output files for this case. And if you would like to ask questions or anything is unclear, please always email us at support@petrologsoftware.com. And in the next tutorial in this series, we will consider an even more complicated case when we have volatile elements present in the magma as well.